For this video, I'm going to focus on a lot of the topics relating to matter, the different types of matter, phase changes, and even physical and chemical properties and changes. So this section has a lot of vocab that you really need to focus on. It's not a math-heavy section. It's very vocab intensive with examples and stuff like that. So you really need to make sure you're studying and remembering the vocab here. So matter is anything that has mass and takes up space. So it has to have those two requirements, right? Basically, has to have mass and volume. So matter would have a density associated with it. Just two terms here to start off, mass and weight. Technically, they are not the same. That's what this symbol means down here. Mass and weight are technically different. Mass is the measure of the quantity of matter, and weight actually relates to gravity, the pull of a given mass due to gravity. So if you're trying to remember these two, just remember weight always has to do with gravity. So technically, there is a difference between the two. They're not interchangeable. Physics, this would be a big deal if you say mass when you really mean weight. For chemistry, we kind of use them interchangeably, even though technically they aren't really interchangeable. You should be familiar with the three states of matter, solid, liquid, gas, so that's not really anything new, but you should be good with some of these characteristics here as well. Solids have a definite shape. That means the shape of a solid is not just going to change on its own. It keeps its shape. Whatever the shape of a solid is today, it would be that exact shape tomorrow. And its volume is definite as well, which means its volume is not going to change. Solids typically have a high density because they have a lot of stuff in a given area. Therefore, they're not easily compressed. And you need to realize here that all three states of matter have moving particles. It's just that in a solid, those particles are moving very slow. And then when you get to a liquid here, liquids have an indefinite shape. So that means the shape of a liquid can change. If you put, 100 milliliters of water in a cup, it would take the shape of the cup, but it'd be 100 milliliters. If you were to, throw that 100 milliliters on someone, now the water is the shape of that person. So the shape changed, but it's still the same volume, would still be 100 milliliters. So the shape can change, but the volume is going to be definite. And it's not, as easily compressed. There is a little bit more empty space in a liquid, but it's not easily compressed still. Its particles would be moving a little bit faster than a solid here, but definitely way different from a gas. Gases have an indefinite shape and an indefinite volume. So gases will take the shape of their container, and their volume can expand. So if you have a gas in a container, it's the shape of the container, it's the volume of the container. As soon as you open up the lid on that container, the gas will now take up the space of the entire room, and it will be the shape of the entire room. So we say indefinite shape, indefinite volume for a gas. Gases therefore have a low density because they don't have as much stuff in a given area, and therefore then they can be easily compressed. And the particles of a gas are moving much faster here. All right, so you need to understand here that in terms of the speed, gases would be the fastest, liquids are in the middle, and then solids would be the slowest. And a vapor is just a term here. It's this gaseous state that could be liquid or solid. So you should be very familiar with solid, liquid, and gas. These pictures here give you a better idea of the three states of matter from a particle view. So if you took a solid and put it in a beaker, notice the solid does not take the shape of that beaker. They are nice, organized, arranged here, very little empty space in there, kind of perfect arrangement. That's what you would expect for a solid. A liquid in the beaker takes the shape of the beaker. It's not as organized. There's a little bit, more empty space here, but still not much. It's a little bit more unorganized than a solid, but still, somewhat organized. And the particles would not be moving that slow, but they're not like zooming around. And notice the difference here between a gas. You would actually have to have the lid on this beaker. The gas particles have much more empty space in between them. They'd be moving around much quicker, hitting the walls of the container, hitting the lid. Definitely not as organized. So the kinetic molecular theory basically says that all matter is made of these, small particles, and that these particles, these molecules, are in constant motion. It's just that for a gas, they're moving much faster. I like the picture on this slide as well because it does show you this difference here between the solid, liquid, and gas in the kind of particle level. So if you look here, the zoomed in view of this crystal of salt, you can see that it's very organized, very arranged, very little empty space for a solid. Liquids have a little more empty space, not as organized compared to a solid. And then gases, a lot of empty space. And they're trying to show you there that those gas particles are moving around, constant motion, hitting each other, hitting the walls. All right, so this definitely gives you a nice view of all three, and you should be familiar with the states of matter here from a particle view. Phase changes occur anytime you switch between these states of matter. So anytime you're going from like a solid to a liquid or a liquid to a gas, that's called a phase change. And the way this happens is you just add or take away energy. So if you look here on the left, you can see that solids are the lowest in energy. They have the slowest moving particles, so they're the lowest in energy. Liquids are kind of in the middle, and then gases are in the highest energy because those particles are moving around much quicker. So if you wanted to, freeze something, if you wanted to freeze water, think about what you would do. You would make it colder. You'd put it in the freezer, right? So in order to do that, you'd have to take away energy. You put it in the freezer. If you had liquid water and you wanted to get it to turn to a gas, you would put it on the stove, heat it up. All right, you'd add energy to get it to go to a gas. So all you're doing to get a substance to change phase is add energy or take it away. I'm just going to quickly go through these phase changes. These should be very familiar to you. You probably know most of these already. So anytime you have melting, that's when a solid goes to a liquid. Okay, so we are adding energy here. So there's a question here on the bottom. What is the melting point of water? Technically, the melting point of water, if we do this in Fahrenheit, would be 32 degrees Fahrenheit. All right, so anytime you go from a solid to a liquid, that's melting. Freezing is the reverse of melting. So that's when you have liquid going to a solid. And then the follow-up question here, what is the freezing point of water? Technically, the freezing point of water is also 32 degrees Fahrenheit. All right, so the freezing point and the melting point are technically the same. If you got really technical, would one be like a little above and the other be a little below? Maybe, but technically they're considered to be the exact same temperature. Evaporation is when you have a liquid going to a gas. So think about you have a puddle out on the street on a hot summer day. As the sun hits it, eventually it disappears because you're adding energy and you're turning into a gas. So very important to understand that this evaporation process is very important for sweating. All right. People think that when you sweat, that the water is what's cooling you, but that's not actually true. When you sweat, the water covers your skin, and as the higher energy particles evaporate and turn to a gas, you start to feel cooler because the lower energy particles are left behind. So remember, gases are higher energy. So as the liquid covers your skin and starts to evaporate to turn to a gas, the higher energy particles leave and the lower energy or the cooler particles are left behind on your skin, and you start to feel cooler. So anytime you have a liquid going to a gas, that's evaporation. Condensation is the reverse here. It's when a gas goes to a liquid. So you probably experienced this when you take a hot shower and you get out and the mirror has kind of fogged up from all the gas condensing to pure liquid water on the mirror. If the mirror was clean before you got in, that would be pure water on the mirror. You could take a drink and it would be pure water. So condensation is gas to liquid here. People aren't as familiar with sublimation. This is when you have a solid going directly to a gas. Some substances are able to do this, at room temperature, where they can just bypass the liquid phase completely and go directly from solid to gas. So dry ice is a great example of this. Dry ice is solid carbon dioxide that will go directly to gaseous carbon dioxide. So it's still carbon dioxide, it just goes from the solid form directly to the gas form. And it keeps things cold, very similar to how we talked about the sweating process here. As the higher energy particles, turn to a gas, the lower energy particles are left behind, so it keeps things cold. This is a very efficient way to ship things that you want to stay cold because they're not going to be soaked in a liquid, but you do have to make sure it's vented properly, otherwise it could technically, blow up here. Another good example of sublimation are those little air fresheners you might have around. They're kind of a solid substance and they will turn directly to a gas and start to disappear over time. Sublimation is anytime you have a solid going directly to a gas. There's some more terms here we can use to describe matter. So the last few slides here are going to focus on specific vocab that you need to focus on with examples. So we did kind of already talk about intensive properties when we talked about density. Intensive properties depend on the type of a matter, not the amount of it you have. So we said, like, if you had, a large amount of gold and a tiny flake of gold, uh, they would both have the same density because they're both gold. How much you have does not matter. So these would be other things like color. Color would stay the same no matter how much you had of a substance or melting point or hardness. And then extensive properties, these depend on the amount of matter present. If you think about it, the mass or the volume here of a substance would specifically depend on how much of that substance you had. So I always just remember in my head EA, extensive, the amount matters, EA. All right, so you need to definitely know the difference of these with examples. If you wanted to give an intensive property of this bowling ball, you could talk about the color of it. If you knew the melting point, you could talk about that. An extensive property of these silver bars, you need to get out your balance and put them on there and see how much uh, they weighed. So these are definitely some terms that you need to know with examples. There's two different types of properties here, physical and chemical properties. Physical properties are these qualities that you're observing or measuring without changing the substance's composition in any way. So you need to understand that physical properties are observations here. You're looking at a substance, observing it without changing it in any way. So these would be things like state, color, melting point, density, basically like you describing a substance. So like if you looked at this grass here, you could say it's green. Right? You're just observing characteristics about this without changing it in any way. A chemical property, on the other hand, is still an observation, but you could only observe it if the substance underwent a chemical change. All right, so this is very important to understand. They're both properties, they're both something that you're observing. It's just that a chemical property you could only see if it underwent a chemical change. It's still a property, though, it's still something you're observing. So these are a lot of times things like the ability to do something, like the ability to oxidize. Oxidize is another word for rust or tarnish. So if you said iron has the ability to rust, that's a chemical property. It's not saying it actually rusted, it said it has the ability to do that. So you would only see it if it underwent a chemical change. If something is flammable, you're not saying it's burning, you're saying it has the ability to catch fire. Or if something had the ability to ferment. So these logs here would be flammable. They have the ability to burn. That's a chemical property. I could only observe that if it underwent a chemical change. So you got to be very careful here. If you're asked to give a physical or chemical property, make sure these are things that you could observe, for a physical property without changing the composition. And a chemical property, you have to observe it only if it underwent a chemical change, but they're both observations. And the last thing here are the two different types of changes, physical and chemical changes. Notice these are different from properties. These are when the substance actually changes. A physical change is when you might change the way something looks, but you're not changing the composition or what it is. It's still the same substance. So we say that physical changes are reversible because you did not change the substance. Maybe you just changed the way it looked, but it's still the same substance. All right. So these would be examples like cutting, melting, freezing. Any phase change would be a physical change. Just remember, pH phase change, pH physical change. So even something like sublimation, you take a solid going directly to a gas. People think, oh, that can't be a physical change. It's still the same substance because it's a phase change. Solid carbon dioxide, dry ice, goes to gas, carbon dioxide. It's still carbon dioxide. All right. Take water and freeze it. It's ice, but it's still water. You didn't change what it was. You just changed the way it looked. All right. And then a chemical change is when you change the composition of the matter. So basically, you get a new substance. That's the key here. In order for a chemical change to take place, you need to get a new substance. So chemical changes are what we say irreversible because the only way you could get the substance back is if you underwent another chemical change. So something like cooking food. Anytime you're cooking food or burning something, that's going to be a chemical change. You get new substances. Photosynthesis is a great example of that. You have substances coming in, you have new substances coming out, and you're making the food here for the plants. Rusting is a good example. All right. So you got to be careful here. If you're asked to give like a physical property, you can't talk about the changes. Properties are just observations about the characteristics. All right, changes are when the substances actually change. So physical change, you change maybe the way it looks, but it's still the same substance. Chemical change, you get a new substance. So this burning match here, that would be a chemical change because you get a new substance or substances. All right, you're turning into new gases. You get some soot being given off, so you definitely get new substances. What about if you just cut this egg? Would that be physical or chemical? It's going to be physical. All right, all you're doing is cutting the egg. But when you cook the egg or hard boil the egg, that's going to be a chemical change because you're cooking it. But boiling the water would just be a physical change. So be careful. And then if you just cut these strips of paper, that's going to be a physical change. So in order for it to be a chemical change, you need a new substance to form.